All right, for a specific reaction, I'm going to choose one that actually has a bit of a challenge for us. So this is 1-chloropropane. And what would you predict as the product based on the general reaction we had a few minutes ago? Well, you probably should come up with, and could come up with, propylbenzene. But that's not the only product. We also obtain isopropylbenzene. In fact, in many instances, this will be the major product of the reaction. Well, how can that be? To understand this, we need to begin to look at the mechanism of this reaction. So, chlorine, of course, has lone pairs there. And remember, we said aluminum chloride is our Lewis acid activator in this reaction. So we form a Lewis acid, Lewis base adduct. This, of course, would be a reversible or exchangeable coordination. This produces this species. Now we can write this as minus plus here if we look at the formal charges in the system. And this can, of course, undergo rearrangement. Remember carbocation rearrangements? Now, I'm not sure how you have been taught, but we don't formally, in solution synthesis phase reactions, solution phase reactions in normal syntheses, form carbocations. But for pedagogical purposes, I'm going to illustrate this as a dissociation. And I'm going to put this as a carbocation. Now I'm going to put quotes around it because I want you to understand that in a simple synthetic reaction in solution, primary carbocations are too high energy, but pedagogically this helps us understand tremendously what's going on. Now, remember carbocation rearrangements and carbocation stabilities. What was the order of stability of carbocations? Well, remember that tertiary carbocations were more stable than secondary carbocations. Those are actually much more stable